So the second part of atomic physics, we are going to start looking at the Bohr model of the atom, which means we're going to have to talk about continuous spectra, line absorption and line emission spectra, and also energy levels or energy states. We're also going to talk a little bit more about the de Broglie hypothesis and also the quantum mechanical model. So let's delve into this one right away. So Niels Bohr, you may have heard of him in Science 10 when you had to do the Bohr model of the atom. So he worked under Ernest Rutherford, and they recognized that, him and Rutherford recognized that the planetary model, or the Rutherford model, had a really, really serious flaw that Rutherford knew about but kind of went, whatever. Now, according to the planetary model, we have electrons orbiting in a circle around the nucleus. Now, we know from circular motion, those electrons are going to be accelerating. We also know from the previous unit that charged particles, which an electron is, that accelerate will produce electromagnetic radiation, or will emit electromagnetic radiation. So what's the problem? Well, electrons orbiting a nucleus, they are going to be emitting electromagnetic radiation. So as they emit EMR, they should start to collapse into the nucleus, which means we shouldn't have any stable matter. We know that doesn't happen, so we have to figure out why that doesn't happen and how we correct this flaw, because that's a pretty big flaw. We can't just overlook that. So Bohr and Rutherford tried to figure out what this was, and what they ended up doing is they ended up looking at this different branch of physics to find the solution. And this came through a conversation between Bohr and his colleague Hansen. So Hansen had returned from Germany to study this thing called spectroscopy, which looks at the light emitted and absorbed by different materials. So what Hansen had told Bohr is that the wavelengths of light in the spectrum of hydrogen, they have a mathematical pattern, but nobody could explain why it had a mathematical pattern. And here's the thing, Bohr realized at that moment, spectroscopy, this whole studying of light emitted and absorbed by materials, it had to deal with the solution to correct the Rutherford model. So let's kind of look at that in a little bit more depth. So before we get into spectroscopy, we have to talk about the different type of spectra. So any hot, dense material is going to emit a continuous spectrum of light. So what that means is we're just going to see all the colors in a continuum. So like for example, the sun itself, it emits a continuum of light. We only happen to see certain colors due to something called Rayleigh scattering. Now here's where we're going to look at the more interesting parts, this emission spectra and absorption spectra. So the first case here, we're going to have a high voltage source. We're going to apply a voltage across a low pressure gas. What that's going to do is that's going to heat up this gas. And what we'd like to do is we'd like to take this heated gas and we'd like to pass the light from it through a diffraction grating. So what's going to happen is that we are going to notice specific bands of color. What we notice is that we're not going to notice a continuous spectrum, we're just going to notice some particular bands of color at particular wavelengths. So these discrete lines that we're going to observe, these are referred to as emission line spectrum. So here you can see for the different elements, they have different emission line spectra. So if we pass hydrogen gas through diffraction, if we heat up hydrogen gas and pass it through a diffraction grating, this is what we're going to see. We'll see this for sodium if we do the same thing for helium, for neon, mercury. Each individual element has its own unique emission line spectrum. We can kind of think of it as like the atomic fingerprint of the element. So if you have an exact match, you know what element you're going to have. Now, we can kind of flip this around and we can look at something called the absorption spectra. So what we're going to do instead is we're going to take a cool gas here. So this is going to be a cool gas. We're not going to apply any heat to it. We just want to kind of leave it as is. And we're going to pass that gas through white light. And then you'll see here we have this almost white light. And I'll explain that in a minute. And we're going to pass that through a diffraction grating. What you're going to notice is that you should see a continuous spectrum almost minus some dark bands. So those dark bands, these are referred to as the absorption line spectrum. What happened here is when we passed that gas through the white light, those wavelengths of light were absorbed in this gas, and then we can't actually see them. They're absent on this continuous spectrum. Now one might ask, well, what's the link? The absorption spectrum and the emission spectrum give you the exact same information. So for example, we have mercury here. So if we pass heated mercury through a diffraction grating, we're going to see these particular wavelengths of color on an emission line spectrum. On an absorption line spectrum, if we pass cool mercury through white light and then pass that through a diffraction grating, we'll see the continuous spectrum, but we'll see the absence of color at particular wavelengths. So this absence of color in the emission line or in the absorption line spectrum corresponds to the same wavelengths in the emission spectrum. So they tell you the same information. So the emission line spectra and the absorption line spectra tell you the exact same information. They just present it in slightly different ways. So that is just something to be aware of. So this is going to lead us into Bohr's model of the atom. So we want to see how he ended up correcting Rutherford's model. So in short, Bohr proposed a few things. First of all, he proposed that electrons, they can only orbit the nucleus at specific distances from the nucleus. So they're locked in place. We would say that those orbits are quantized. They can only be at a particular value. And then he also stated that the kinetic and electric potential energies of an electron in orbit depends on the electron's distance from the nucleus. So energy depends on distance from the nucleus, but if we fix that distance from the nucleus, if that can only take on specific values, we can also say that the energy only takes on specific values. So we would say that the energy of an electron in an atom is also quantized, and each orbit represents what we call a particular energy level for that electron. And an electron can move between the states, but it can only do this by either emitting or absorbing a photon, and it has to have energy that is equal to the difference between the two energy levels. And that's what we're going to look at in a minute. If the electron happens to stay in a particular orbit, it will not radiate energy. And if it's staying in that same state, we're going to say it's in a stationary state because its energy is not changing, its distance from the nucleus is not changing. Now, sometimes you may see this n number here. This n is referred to as the principal quantum number. It basically just tells us the size and energy of a particular orbit. Now, those of you that end up doing first year chemistry in university, you're going to go a lot more in depth with this. You're going to start talking about like the Balmer formula and the Rydberg constant and all that. We're not touching on that. This is just to kind of scratch the surface a little bit. So let's look at what's going on in the Bohr model. The Bohr model basically, if we could kind of use a phrase, it's all about energy level transitions. So in the Bohr model, we're looking at electrons transitioning between orbits either by emitting a photon or absorbing a photon. And he was able to explain absorption and emission line spectra for hydrogen and other elements using these ideas. So if we would like, for example, an electron, if we want it to move from a lower energy level to a higher energy level, what's going to have to happen is it's going to need to absorb a photon. And that photon has to have energy that matches the difference between the energy levels that the photon or the electron's traveling between. And since those electron energy levels are discrete, that difference between them, it's going to correspond to a particular frequency value because we know that E equals HF, that Planck formula. So only the photon with the correct frequency is going to be absorbed. So on your absorption spectrum, this is why you're going to see dark lines at particular frequencies because you're seeing transitions at particular frequencies that are the perfect frequency match to go between those orbits. Now, if you want to kind of go the other way around, you want to move from a higher energy level to a lower energy level, you need to get rid of a photon or you're going to emit it. And again, the energy of that photon that's ejected, it has to match that difference in energy between the energy levels of the two states that you're going between. And what this means is that it's going to correspond to a photon with a particular frequency. So this is why for emission spectra, you're only going to notice colored or you're going to only notice light at particular wavelengths. Those wavelengths of light that you see correspond to the photon being emitted at those particular frequencies, or we could say wavelengths. Those of you that study spectroscopy in a bit more detail, you may learn about things called the Balmer, Lyman, and Paschen series. These just happen to deal with transitions between particular states. So for example, in an electron diagram, or in an energy level diagram, we have this n equals 1, the ground state, then the next one above it, n equals 2, 3, 4, 5, 6. So what we would say is that if we're going from any higher state and our final state is always the ground level, we call this the Lyman series. Usually this deals with UV. Balmer deals with anything transitioning from a higher state to a state ending on n equals 2. And then Paschen deals with anything coming down to the state n equals 3. You do not need to know these spectra by name, but if you do study these in university, you will see this come up. So let's look at an energy level diagram. So the ground state is the first energy level. So I'm just going to put that here. First energy level. So the ground state is going to be the first energy level. Now, let's look at this. So first of all, we want to see the number of photons of different wavelengths that we could produce for an electron at level C to get to the ground state A. Well, okay, the first one, we could go directly from C to A. That works. We emit a photon with energy difference, with the energy equal to the difference between these two states. That certainly works. Maybe it takes a more convoluted path. Maybe first of all it goes from C to B, and then it goes from B to A. So instead of going the direct route, it kind of takes a bit of a detour, or it kind of takes a bit of a stopover. So instead of going directly C to A, we go C to B, then B to A. So in order to go from state C to A, we have 3 different photons that can do this. So let's determine the energy that happens to be released as an electron makes the transition from state D to state A. So as we go from D down to the ground state, so that difference in energy is going to be the energy of the final state, which in this case is A, minus the energy at state D. So at A, we have negative 15 electron volts, and we're going to subtract off our initial energy of negative 3. So that is going to give me negative 12 electron volts. So that negative here, that tells us energy is released, which means a photon is being released. So what has to happen if we have a photon going between if we have the transition from state D to A, 12 electron volts of energy are released. So the frequency of that photon is going to correspond to that energy level. We can calculate again that frequency using E equals HF. So we can also do the case of an absorption. Let's find that absorption going from state B to C. So that difference in energy level is going to be the final minus the initial. So we're ending on C and we're starting on B. So at C we have negative 8 electron volts. At B we have negative 11 electron volts. So this is going to give us positive 3 electron volts. What this is stating is that with the positive, energy is absorbed. So we need a photon that has 3 electron volts of energy in order to go from state B to C. So D is a little bit of a trickier question. So D, we have an electron in the ground state in an atom. It's struck by a passing electron. And this electron has energy of 10 eV. And the atom's electron absorbs as much energy as possible. So we'd like to find the kinetic energy of the passing electron after it collides with the atom and the minimum possible wavelength of light that could be released from this atom. Right, so what's kind of going on in here? So kind of like here's our electron in the ground state, and it would like to get up to a higher state. So we're going to have an electron coming in. We know that this electron, we're told it has 10 electron volts of energy. So it's going to collide with this electron. It's going to impart some energy on it so that it can go up to a higher state. And then this electron is going to leave whatever energy it gives to this electron here, it's going to be deducted from that 10 eV. So this electron that passed by is going to have so much kinetic energy left over. And then what it gave to that electron, it's going to help it get to a higher state. We want to see how much energy it can take. So we have to go back to our diagram here. So our energy level diagram, we're at the ground state. The electron, we're told, can take the most amount of energy. So what we want to see is how far up the ladder it can go without going over the energy. So to go from negative 15 to negative 11, this is going to require 4 electron volts of energy. Now, we have 10 available to us. 4 is good. Can we take more instead? So to go from A to C, well, to go from negative 15 all the way to 8, that's going to require 7 electron volts of energy. So we can go to state C. We still have energy left over. What about if I try to go from state A all the way to state D? Well, that's going to require 12 electron volts of energy, but that's exceeds. We only have 10 available to us, so we can't go from A to D. There's not enough energy in that passing electron. So that passing electron will allow us to get to state C. So what's going to happen here is that electron is going to come in, this one with 10 eV. So this electron, the ground state, it's going to take 7 electron volts of energy. So that's the most it can take from this electron to get up to its highest state. So if this electron, the ground state, robs this passing electron of 10 electron volts of energy, it's only going to have 3 electron volts of energy left after it passes. So that kinetic energy, the kinetic energy of that electron after it passes, it's only going to have 3 electron volts left. That's how much remains after that electron in the ground state robbed it. So we'd like to find the minimum possible wavelength that can be released from the atom. So the minimum possible wavelength has to deal with maximum energy transition. Well, we just saw the maximum energy transition going between those two states. So the maximum energy transition that can occur based on this scenario is 7 electron volts of energy. There's a difference between the states of 7 electron volts. We would like to find the wavelength that corresponds to 7 eVs of energy. So we know from the Planck formula E is equal to hc over lambda, or lambda is hc over E. Now, with my energy in electron volts, I'm going to use the Planck constant in electron volt seconds just to make my life a little bit easier. So then we'll divide this by 7 eV. So my EVs cancel here, my seconds cancels there. So I am left with something in meters. That's good. Always check your units. That's a really important skill in science because, you know, that can save you from making some clumsy little errors. So we're going to get about 1.8 times 10 to the minus 7 meters. So with that maximum transition of energy, so either going from state A to D or D to A, there's a difference in 7 electron volts of energy. And whether you're absorbing or emitting a photon, that's going to correspond to a wavelength of about 1.8 times 10 to the minus 7 meters. So you'll notice that we're really starting to tie a lot of EMR to this atomic physics unit. Not really a coincidence. Right, just the last thing I want to talk about quickly. Now, you might wonder why we're talking about this. I'll explain that in a moment. So in atomic physics, when we're talking about energy levels of the hydrogen atom, it's governed by this equation here, this En equals E1 over n squared. So En is the energy of the nth orbital. It's in joules or electron volts. E1 is going to be the energy of the ground state, so that n equals 1. And n is going to be that quantum number, that principal quantum number we talked about earlier. Now, sometimes we're very interested in moving an electron completely from the atom. So if we completely remove an electron, this is what we refer to as ionization. Because then if we strip that electron out, we're going to add a positive charge to this atom. So now it's going to be ionized. So when we're ionizing something, what we're doing is we're saying we're taking it to the state n equals infinity. So we're going to say that the electron's infinitely far away. So kind of looking at this formula, this E1 over n squared, well, the energy at an infinite state, we want to think of this as like this E1, it doesn't matter what it is, divided by, well, as we go up to infinity, think of E1 divided by a really, really big number and then square that. So divided by the biggest number you could think of, squared, chances are this thing is going to be so close to 0, and we're going to state that that is 0. So what we're going to say is that the energy of an ionized electron is going to be 0. This is the highest energy required. You need the most energy to ionize something. We've defined this energy as being 0 for convenience sake. This is why on your diagram here, this energy level diagram, we see at ionization we have 0 electron volts. This is why all the energy associated with different energy states have a negative in front of them. Because if 0 is going to be the maximum amount of energy, to have smaller energies below the ionization state, we have to go into the negatives. This is more of a convenience. This is more to help us out with notation and simplify things. This is basically what we would say is kind of like a reference, or it's kind of a convention that they use in atomic physics. So our ionization, or the most energy, we define as being 0, and then we work our way down to the negative numbers to kind of stick with that convention. So last thing, when we're dealing with energy differences in a Bohr level diagram, if energy is absorbed, delta E is going to be positive. If energy is emitted, delta E is going to be negative. If you happen to be using that change in energy for calculations, so like we're talking about like E equals HF or E equals HC over lambda, in those cases, just use the absolute value because we don't deal with negative frequencies and negative wavelengths. So just something to be aware of.